Geology of Fuels Part 2. The accelerated agricultural and industrial growth of our country has posed a serious challenge of meeting the quantitative demand of secure and affordable energy. This vibrant development process is also resulting in a shift from the use of non-commercial energy sources to commercial energy sources, particularly electricity. The problem is in the light of recent developments of global measures to cut emission and emphasis on producing electricity in environmentally benign means. In this context of a planned electricity generation, expansion of nuclear power generation capacity occupies a special standing in countries' endeavor towards energy independence. It has also been established and appreciated in many countries of the world that the nuclear power is a reliable, environmentally benign and economically viable source of energy. Accordingly, our country is on the preferred path of generating nuclear power with the use of indigenous atomic mineral resources. In this chapter, we will focus on the geology of atomic minerals, rare elements and rare metals found in India, their uses and industrial applications. Atomic minerals. Atomic energy is produced by fission, splitting of the radioactive elements like uranium, or by fusion like colliding and fusing of two deuterons of form helium of atomic nuclei, with matter being converted into energy in either process. Atomic minerals are the minerals of radio elements, mainly uranium and thromium, and those in which these radio elements are in minor to trace amounts. These radio elements are associated with major contents of rare metals Rm like niobium, tantalum, NbTA, beryllium Be, lithium Li, zirconium Zr, etc., and rare earth elements REEs, lanthanum La, tellurium Lu, as the radio elements exhibit the characteristic property of radioactivity. The atomic minerals are also generally known as radioactive minerals. Radioactivity. It is the property possessed by certain elements of high atomic weight like radium Ra, thorium Th, and uranium U of spontaneous emissions of radiations of alpha 4 2H2 He2 plus particles, beta high energy electrons accompanied by neutrons particles, and gamma high energy short wavelength X-rays, rays due to the disintegration of the nuclei of the atoms. Example, 238U decays finally into 206 Pb. These radiations are capable of penetrating opaque bodies and affect a photographic plate even when separated by a thin sheet of two metal. Uranium U atomic number Z to 92, thorium Th Z minus 90, and potassium K isotope of mass number 40 K constituting 0.012% of K are the naturally occurring radio elements. Thorium Th with atomic number 90 has 6 isotopes. Of these, the most abundant and longest lived is 232Th. The isotope 232Th absorbs slow neutrons and is converted to 233U. This in turn is fissionable and hence can be utilized as a nuclear fuel in breeder reactors. This indeed is the third stage of India's third stage nuclear power plant. Uranium U with its atomic energy 92 is composed of three principal isotopes: 234U 0.0054%, 235U 0.720% and 238U 99.275%. 235U undergoes fission with slow neutrons and can sustain a chain reaction with release of enormous amount of energy. 235U on increased content from 0.72% to about 2.5 to 3% constitutes the enriched fuel for light water nuclear power reactors such as the Tarapur reactor. 238U like 232Th absorbs slow neutrons to form 239U. This in turn decays to 239Pu plutonium that can sustain a fission reaction and thus can be used as nuclear fuel like the one used in many heavy water moderated nuclear power reactors such as at Kota, Narora, Kakrapar, Kaiga, etc. Concentration of U, Th and related elements in the Earth's crust. The occurrence and concentration of different elements in the Earth depend mainly upon their geochemical coherence, that is, elements with similar or comparable chemical properties of ionic radius, ionic charge, electronegativity, etc. occur and concentrate together. Thus, uranium with its charge of 4 plus and 6 plus and corresponding ionic radii of 0.89 and 0.73 A and Th with its charge of 4 plus and ionic radius of 0.99 A go together with the elements of same or nearly same charge and or similar ionic radii. During the evolution of the Earth, much of all these elements being incompatible with many other elements of greater abundance was expelled from the mantle and core and concentrated in the shallower crust. Accordingly, the crustal rocks of acid, magmatic and their derived products of sedimentary and metamorphic rocks contain higher concentration of these elements. The average abundance of U and Th in the Earth's crust upper part is respectively about 2 and 8 ppm, with the value of Thu being between 3 and 4. Their average abundance in the deeper parts of the Earth, viz. Mantle and core, is much less, since all the three radio elements U, Th and K, 40K, concentrate progressively in the crustal part. U and Th contains in the common rock types. In the common rock types, both U and Th prefer acidic with high silica content of lesser 62%, especially alkali, K and Na, rich magmatic rocks, carbonaceous and phosphatic sedimentary rocks, and third, prettiferous FeS2 quartz pebble conglomerate and low medium grade, temperature lesser than 350 degrees centigrade, metamorphic rocks of phyllites and schists with Thu value ranging from lesser 1 to 5. Like U and Th, potassium also is relatively more in the crust, average 1.2%. Determination of radio elements K, U, Th and total in a sample from an area of radioactive anomaly is carried out either by radiometric analysis using gamma ray spectrometry or chemical analysis. Accuracy of such estimates depends on radioactive equilibrium in the radioactive series, as it is based on the measurement of gamma or beta radiation from the daughter products in the decay series of Th and U, and not directly U or Th, since both these alpha emitters. Thus, by counting the beta or gamma rays emitted by some of the daughter products of U or Th, the quantity of the parent in the sample is inferred. Atomic radioactive minerals. Atomic or radioactive minerals are discrete minerals of uranium and or thorium, or exemplified by uranite or U and thorite of Th. Besides, they include those in either U or Th or both occur in notable quantity, like the minerals of rare metals Nb, Ta, Li, Be, Sn, W, etc. and rare earth elements Ree, La to Lu, Y. Formation of atomic radioactive minerals. Geochemical processes play an important role in the formation of minerals. Uranium forms a major constituent in many minerals of its own. In contrast to U, Th mineralogy is relatively simple, as only one principal oxidation state of thorium, Th4+, is of importance. Th commonly replaces Zr in zirconium minerals, Y, Ce and other Ree in most Re minerals, and U in certain U minerals under conditions of relatively higher temperatures. Primary and secondary atomic radioactive minerals. Radioactive minerals are broadly divided into primary and secondary discrete minerals of U and Th, and nearly 200 such minerals are known. The primary minerals are those formed directly from magmas, hydrothermal solutions and groundwater. Secondary minerals are formed due to remobilization of elements from primary minerals, their transportation in solution, and later precipitation due to oversaturation in oxidizing or supergene surface or shallow surface environment. The most common primary minerals of uranium are uranite, pitchblende if microcrystalline, oxide, coffinite, silicate and branerite, complex oxide. The most common primary minerals of thorium are thorianite, throuranite, oxidized and throite, uranothroite, silicates. A few secondary supergene minerals of Th are known, the most common being thorogumite. Location and identification of atomic radioactive minerals. As the atomic or radioactive minerals usually occur in low content, lesser 1% in rocks, they are difficult to locate and identify by normal megascopic and microscopic techniques. These are used in identification of rock forming minerals that occur in major to minor quantities greater 1%. However, the intrinsic property of radioactivity resulting in spontaneous emission of alpha beta particles and gamma rays of Rm is taken advantage of for their location as well as estimation of the contents of Eu, U and Th. Thus, location of Rm in a rock sample is done by the technique of radioluxography (RLX) or solid state nuclear detection. The latter is a modified and easy version of the former. Exploration for atomic radioactive minerals. Nature of exploration. Exploration for atomic radioactive minerals (Rm) encompasses diverse techniques in the disciplines of geology, geophysics, geochemistry, geostatistics, remote sensing, aerial surveys, instrumentation physics, analytical chemistry or petrology, mineral technology, survey, drilling and exploratory mining. These are carried out as field and laboratory based investigations. They are simultaneously undertaken starting from regional level and ending with establishment of an economically workable mineral deposit. Uranium. Compared to the exploration of other metals like Fe, Mn and Al with grade of 30 to 70%, exploration of uranium is unique in that even very low concentration of 0.1% U308 are economical to work. Based on geological setting and multidisciplinary evaluation, sites selected. These are integrated with their radioactivity. Such radioactive sites are explored for Rm. Thorium. For establishing Th mineralization in the form of monazite as well as its associated placer minerals like ilmenite, rutile, zircon, garnet, sillimanite, etc. Drilling is carried out on sand deposits. These are mainly coastal like on the east and west coasts of India and minor inland like in Tamil Nadu. Such deposits are drilled in both the dry zone, that is both water table, and wet zone below water table and even in the lake bed. Rare metals, rare earths. In prospecting for RMRE deposits, mobile ore dressing plants are operated in the field of pre-concentrate rare metals like NbTA and Y and heavy REE bearing xenotime and light REE bearing monazite in the gravel. This pre-concentration is carried out before final industrial scale recovery. Mining for atomic minerals. After establishing a deposit, it is to be mined. The mining is carried out first on an exploratory scale and then on industrial scale, either by open cast or underground methods. Selection of these methods depend upon various factors like depth of mineralization, its grade and tonnage, ore characteristics, available infrastructure in the area, and environmental ecological considerations. The ore obtained thus is treated on an industrial scale in a mill for recovery of metals like U. Major deposit types of atomic radioactive minerals with Indian examples and resources. Occurrence of atomic radioactive minerals in diverse rock types. Radioactive minerals occur in very low abundance, usually less than 1% in different rock types. In first, magmatic or igneous rocks. Number 2, sedimentary rocks. Number 3, metamorphic rocks. In the magmatic rocks, they usually concentrate in acidic SiO2 less than 62%. Plutonic deep-seated rocks, which include granitoids, pegmatites, and volcanic rocks like rhyolites and acid tuffs. Radioactive minerals like monazite and zircon also occur in places derived from such magmatic rocks. Among the sedimentary rocks, sandstones, pyrite-bearing quartz, pebble conglomerates, and phosphatic and carbonaceous rocks are good hosts for uranium minerals. Low and medium grade. Low medium temperature less than 350 degrees centigrade. Metamorphic rocks like phylites and schists subjected to metasomatic alterations involving additions of volatiles H2O, OH, F, Cl, CO2, etc. within structurally weak zones are the loci for uranium minerals. Accordingly, terrains with these rocks are usually explored for uranium minerals. Thorium minerals occur generally in acidic igneous rocks and high-grade granulite facies, metamorphic rocks, and places derived from these rocks. Major types of uranium deposits in the world. Based upon the geological setting and economic significance, the International Atomic Energy Agency IAEA has classified the following 15 types of uranium deposits in decreasing order of importance. Number 1, unconformity related. Number 2, sandstone. Number 3, quartz pebble conglomerate QPC. Number 4, veins hydrothermal. Number 5, breccia complex. Number 6, intrusive. Number 7, phosphorite. Number 8, collapse breccia pipe. Number 9, volcanic. Number 10, surfacial. Number 11, metasomatite. Number 12, metamorphite. Number 13, lignite. Number 14, black shale, and 15 other types. Uranium deposits in India. Of the above 15 types, the types of U deposits established so far by AMD in India are hydrothermal, vein and disseminated. Second, sandstone. Third, unconformity proximal. Fourth, strata bound carbonate hosted, rare. And 5, albitite, while QPC and phosphorite types occur at prospect levels. These different types of U deposits with variable tonnage and usually of low grade, less than 0.1% U308, occur in different states of India. Vein and disseminated type. This type accounts for much of the uranium resources in the country. It mainly occurs in the Singham Shear Zone SSZ in the state of Jharkhand and to a limited extent at Gogi in the state of Karnataka. Sandstone type. The sandstone type uranium mineralization occurs in first the upper Cretaceous 100 Ma Mahadek sandstone in the Domestent Vakaren area in the state of Meghalaya, and number 2 the Neogene less than 35 Ma Sivalik sandstone along the foothills of Himalaya in the state of Himachal Pradesh, Uttar Pradesh, Uttaranchal and Jammu and Kashmir. Unconformity proximal type. This occurs in the Lambapur, Padagattu, Chitirial area in Andhra Pradesh. It occurs in the northeastern part of the intracratonic middle Proterozoic 1700 to 1100 Ma Kudapic basin on either side of the unconformity between the basement biotite granite and its overlying Sirisalem Banganapale quartzite, strata bound carbonate hosted type. This deposit is hosted by phosphatic siliceous dolostone of the Wampale Formation along the southwestern margin of the intracratonic Kudapek Basin in the state of Andhra Pradesh. It is rather a rare deposit since carbonate rocks are considered as unfavorable hosts for U. Albitite type. This appears to be a potential type. It occurs in the Rohil, Kateshwar, Kandela area in the state of Rajasthan. The uranium mineralization occurs in diverse rock types that are albitized along structurally weak zones. There is a possibility of recovering Ag as a byproduct of U from this deposit that is still under detailed exploration. Other types. These include the pyrite ferrous quartz pebble conglomerate QPC type at the base of Dharwar supergroup and overlying the Archean basement at Valkunji and Chikmagalur, and similar type but hosted by meta-arenite at RBL and Dabguli, all in the state of Karnataka. Second, the phosphorite type in the Mussoorie area in the state of Uttaranchal and Maldirio in the state of Uttar Pradesh. From these, U can possibly be recovered as a byproduct. Since the Proterozoic intracratonic basins like the Kudapa and Bhima host diverse types of U deposits with notable tonnage and grade, detailed exploration by AMD is being carried out in other similar basins like the Chhattisgarh, Gwalior, Vindhyan, Kaladgi, Badami, Pranita, Godavari and Abhumar. Thorium deposits in India. Thorium deposits containing the Th bearing mineral monazite associated with other placer minerals like ilmenite, rutile, zircon, garnet and sillimanite occur at many places along the east and west coasts of India. Notable ones of these coastal heavy mineral sand deposits are at Chatrapur, Gopalpur in Orissa, Bhavnapadu, Kalingapatnam, Sri Kumaran, Bhimunipatnam in Andhra Pradesh, Manva Kuruchi, besides Theri inland places in Tamil Nadu, Chavara in Kerala and Ratnagiri in Maharashtra. Rare metal, rare earth deposits. Columbite, tantalite for NBTA, cassiterite SN, spodumene, lipidolite Li and beryl Be occur mainly in the pegmatite belts of Bastar, Chhattisgarh, Malkagiri, Orissa, Marlagala, Karnataka and in parts of Bihar, Jharkhand and Rajasthan. Besides, NBTA prospects in the form of pyrochlore microlite occur in the carbonatites of the Sangh Valley, Meghalaya and Savatur, Tamil Nadu. Deposits of rare earths in the form of the minerals xenotime and monazite occur in the riverine places of Siri River in the Jashpur district, Chhattisgarh and Dio River in the Gumla district, Jharkhand, besides in the apatite, Re bearing, magnetite veins in Kanyaluka, Singhbhum district, Jharkhand. Industrial applications of atomic minerals. Uranium and thorium. The most important use of radio elements U and T is for production of nuclear energy power. These two are considered as natural resources of primary energy. Fossil fuels with coal, oil, natural gas, which provide over 80% of our energy today, plus U and Th are non-renewable. Electricity generated in the world is mostly from the non-renewable energy resources, plus hydropower among renewable ones, with the rest accounting for very little amount. The conversion of energy into heat values in mega 106 joules mJ, and joule is a unit of energy, of natural uranium in light water reactor 500,000 mJ per kg. The generation of nuclear power presently from U in India, like in many developed countries in the world, is an absolute necessity to meet the ever increasing demands for power. Other highly appealing aspects of nuclear power are Number 1, its very high heat value as compared to other fuels, hence the volume of fuel required is much less, the cost of which is usually comparable or even less than for an equivalent coal-fired power station. Second, clean nature of power with no emission of greenhouse gases like carbon dioxide, methane and halocarbon, CFCs. Third, no site restriction. Fourth, dependability. Other applications. These include production of radiation sources and radioisotopes for healthcare, agriculture, food preservation, industry and water resources besides basic research. Uses of rare metals and rare earths. Apart from uranium and thorium, the nuclear industry requires rare metal and rare earths (RMRE) for many of its operations. The nuclear and other high-tech industrial applications of RMRE are listed below, element-wise. Niobium Nb, Zr 2.5%, Nb alloy for pressure tubes in heavy water reactor, Zr NbCu for garter springs, stainless steel superalloys, superconductors, microalloyed steel industry. Tantalum Ta, capacitors, transmitting and vacuum tubes, heating elements and heat shield, carbides for tools, magnetic films of FeTA or FeNb nitride used in corrosion resistance. Beryllium Be, A, as metal canning material in nuclear reactors, in aerospace and defense, X-ray window, high-speed computer and audio components. B, as oxide electrical insulator, microwave communications, alloys, BeCu in electrical and electronic industries, BeAl as hardener in AlMg alloy, melting. Lithium Li, nuclear fusion, ceramics, glass, battery technology and many chemical compounds. Ree, phosphorus, EuY in CRT, TbGd, La in X-ray, EuSc in lamps, lasers, NdPrHoErTm, superconductors, Y, ceramics, SeYCeLaPr, additive, NdYbEr in fiber optics, Ce for decoloring, NdPrer for coloring, metallurgy, ferrous steels and non-ferrous alloys, superalloys, light Ree for monazite. Nuclear fuel, control rods, reactor components, alloys, superalloys, superconductors, permanent magnets, petroleum industry, mish metal, ceramics, chemicals, illumination, electronics, polishing and coloring glass. Zirconium Zr and hafnium Hf from zircon. HF-free Zr are cladding material in nuclear reactors. Zr as alloys in chemical industry, photo flash bulbs, pigment, ceramics, chemical and compounds, refractories, steel and glass works, toiletries, medicine, tanning and oil. Hf as control rods in reactors.